Hi everyone, welcome back to Info 3370, studying social inequality with data science. Today we're turning into our final course module on interventions to promote equality. In this module we'll be discussing methods for causal inference that help us inform policies. If we could intervene in the world to change something, how might that produce effects that we might want in the socioeconomic distributions that we see? Our learning goals for today's class are to define causal effects using potential outcomes and to understand something known as the fundamental problem of causal inference, which we'll get to as we go on through the lesson today. In this class module, we're going to move from a world where we're just studying the world as it is. We've learned a lot from that place where we described differences in socioeconomic outcomes across subgroups, and we looked at how people's characteristics predict their socioeconomic outcomes. But now we're going to pivot forward into questions about how we might actually change something in the world and produce a change in the outcomes that we observe. As a running example, we'll use the causal effect of education. Here are some figures from Mike Haut's 2012 paper in the Annual Review of Sociology. Haut documents that there are a huge number of socioeconomic outcomes that just look better among those who have more education. So at the right of the x-axis in each of these figures here, we see people with high degrees of education, bachelor's, master's, PhD, and other professional degrees. At the left, we have people with low levels of education. And we see that those with lower education have more unemployment and lower various measures of earnings. When you look at this figure, it raises some questions. Is it the case that people with college degrees earn more? That's descriptively true. We just saw that in the previous figure. But is it also the case that a college degree causes higher earnings? It's this kind of claim on the right that we're now going to consider. When you look at these two claims, you might pause and ask yourself what kind of policies each claim would support. If people with college degrees earn more, that's a useful bit of factual information. But would it support, for example, a policy to expand access to college? Suppose you made more spots in colleges and let more people get those college degrees. Would we expect from the claim on the left that this would produce higher socioeconomic outcomes for those people? It's not totally clear, because maybe it's currently the case that people with college degrees earn more because the people who are the most motivated tend to get college degrees, or the people whose parents have the best connections tend to get college degrees. And maybe these people would have the higher socioeconomic outcomes regardless of whether they went to college. And college is just a marker that doesn't really do anything. But if the claim on the right is true, then if we took people who didn't go to college and we counterfactually sent them to college, then they would actually have better outcomes. And thus that policy would be a good idea. Distinguishing between these two claims is hugely important for both scientific understanding and also for policy. Methodologically, the claim at the left is a claim about two sets of people with two treatments. I'm going to represent that here with this matrix where we're imagining a bunch of rows. Each row is a person, and there are two columns. For each person, there's an outcome that would be realized if they went to college, and an outcome that would be realized if they didn't go to college. The comparison here is between a set of people at the top, all of whom went to college, and their outcome having gone to college, with a set of people at the bottom right who didn't go to college, where we see their outcome that they realized when they didn't go to college. Now let's pivot to the claim at the right. Here we're considering the same people under two treatment conditions. In our matrix now, we have an outcome for every row in each treatment condition. So for each person, we're going to consider how much would they earn in a world where they went to college, and how much would they earn in a world where they didn't go to college. Here you can see that on the left we have what data we always end up working with. We only ever get to see people's outcomes in the treatment they experienced. But a causal claim is about the information on the right, which we can never directly observe. It's about the counterfactual outcomes a person would realize in a world where they went to college and a world where they didn't. We'll use the term factual outcomes to refer to these realized outcomes in the matrix on the left, and we'll refer to the outcomes on the right as potential outcomes, using the language of Imbens and Rubin 2015. When there are multiple potential outcomes, we only ever get to see one of those potential outcomes. In our notation, we're going to use subscripts to indicate people, so here we're looking at person I. We'll use superscripts to indicate the treatment conditions that produce the potential outcomes. So on the right, we have person I's outcome in a world where they went to college and a world where they didn't go to college. So let's work with these a little bit and think about how to translate causal statements to potential outcomes. Someone says, Sarah would have been hired if she had submitted her application on time. Here we have two potential outcomes. Y for Sarah, she's the person in the subscript, in a world where she submitted on time is 1, she would be hired. But in a world where she submitted late is 0, she would not be hired. In class, we went through several additional examples here that I'll just walk through quickly for the video. Perhaps David would have been hired even if he hadn't had a college degree. For David, the outcome under college and under non-college, they're both 1. He was going to be hired either way. There's no causal effect of college on whether David gets hired for the job. Perhaps the hiring manager discriminatorily chose Emily over Lakeisha because of their names. This claim about discrimination is a claim about the outcome for Lakeisha in a world where she's named Lakeisha and she is not hired, compared with a world where we have the same Lakeisha, but counterfactually we imagine that she's named Emily, and in that world she would have been hired. Here we see how potential outcomes let us formalize some complex ideas, like discrimination on the basis of a person's name. Finally, we have an example where Juan never applied because he has a newborn infant. In this world, the outcome for Juan, in a world where he has the infant, is 0. His infant is going to cause him to not apply and thus not get the job. But perhaps in a counterfactual world where Juan had no infant, he would have applied and then he would have gotten the job. Given these examples, we can now ask our question, is it possible to know if each statement is true? So, like looking at the top example, we have this outcome for Sarah in a world where she submitted her application late, and the outcome for Sarah in a world where she submitted her application on time. Can we ever know if submitting the application on time would have caused Sarah to get the job? And we can't from empirical evidence. Empirically, we only ever get to see Sarah in one of those conditions. Likewise, we only get to see David, who had a college degree. We only get to see Lakeisha, who factually is actually named Lakeisha. And we only get to see Juan in the world where he has his infant. If we look at the data across 2 different treatment conditions for a bunch of different people, we always have this problem, where we observe the outcome in only one of those 2 treatment conditions. So could we ever know the effect for person 1? Well, no, we didn't get to see their outcome under control. How about for anyone? Not really. Can anything be known at all? This is a problem known as the fundamental problem of causal inference. Causal effects are necessarily about comparisons for people's outcomes across multiple counterfactual worlds. And yet, in practice, we only get to observe the outcome under one of those worlds. So for each person, it's really impossible to see all of their potential outcomes, and thus it's really impossible to know any individual causal effect. This is a really big problem. So how does one get around it? One way to get around it is to pivot to studying average causal effects. For example, instead of looking at each person's individual causal effect, we might say, let's look at the average outcome under treatment and the average outcome under control. We might be able to estimate those average outcomes under some additional assumptions. For example, suppose here that the treatment was randomized in a randomized controlled trial. If the treatment's randomized, then the observed cases in each treatment condition are a simple random sample from the whole population of outcomes that would have been observed if people had been assigned to that treatment condition. So in an RCT, you can take an average of the observed outcomes under treatment and of the observed outcomes under control, and use that as an estimator for what would have happened to everyone on average if they had been exposed to treatment versus if they had been exposed to control. Averages get us out of the fundamental problem of causal inference once we pair them with additional assumptions about how the treatment was assigned and how that assignment is related to the outcome. Today we've covered the definition of causal effects in the potential outcomes framework, and we've also discussed the fundamental problem of causal inference. Coming ahead in the next classes, we're going to talk about causal assumptions, which will formalize in directed acyclic graphs, and then estimators for causal effects. So that's what's next.